Good morning, everyone.
Good morning.
Hello, hello, great. We're starting shortly. At the moment, there are 18 of us, not that many yet. So let's wait for a few minutes and we are starting, okay? Okay, let us start. Although I'm wondering if there are 25 of us, where are all others? But let's start. Okay, 27 better. First of all, let me outline the next steps, what we are going to do in our course. So if you remember, in the first part, we have done a lot of studies of coordinate transforms. In particular, we're interested in orthogonal transforms, or even more specifically, rotations of coordinate frames. That's because these transforms are very, very widely used in applications. We really have physical examples when there is a coordinate system, and then there is another coordinate system rotated relative to the first one. Remember the airplane example we have seen last time. Today and in the next lecture, we will be studying the geometry of very elementary, as it seems, geometric objects, which are straight lines and planes in the 3D space. So today and next Friday, lines and planes in 3D. Really, they are very, very, very closely connected, and we'll see it today. There are many ways of how lines and planes can be defined using algebraic equations and geometrical properties understood from that. So today it's mostly about definitions and basic equations. And next time, we'll be considering some more or less non-trivial, interesting problems about lines and planes. Although they seem to be very elementary geometric objects, there are, I would say, non-trivial and interesting and useful problems which can be considered about them. And after that, we'll be moving into, I would say, a more exciting area, which will be, first of all, second order curves, also called conics or conical sections in the plane, and also second order surfaces in the three-dimensional space. And after we study them, we will study the applications. I have probably already mentioned, and we started considering some examples from astronomy, from celestial mechanics, that orbital motion in the space, the theory of orbital motion, would connect together all things we have considered so far. So yes, obviously there are lines and planes, for example, the orbital plane. There are second order curves like ellipses, parabolas, and hyperbolas, which are orbital trajectories. And we'll eventually learn the laws of motion of celestial bodies in a so-called two-body problem, when there is a body, for example, a small planet or a spacecraft moving around the central body, like the sun, for example, the center of our solar system, we will be able to derive the equations of motion, predict their orbital position, and then convert that position in the orbit into three-dimensional coordinates, and finally understand how such an object can be observed from the Earth. So the final, probably, well, maybe 3 or maybe 4 lectures, depends on how quickly can deal with other topics. And with these topics, they will be devoted to applications of linear algebra to celestial mechanics, to the extent that we would really be able to do it on paper and in software, prediction of uh, orbital motions in, let's say, in solar system, and calculating the apparent visible coordinates at which a given celestial body can be observed from the Earth or from a given position on the Earth. So that will be an end-to-end application of everything we have learned so far. So the linear algebra theory, which we are dealing with at the moment, it is not just, I would say, something abstract which we learn only to become familiar with it and then do not apply it at all. It is highly applicable, highly relevant, and modern physics, astronomy, engineering, any sciences cannot simply operate without the knowledge of linear algebra. So for today, it is lines and planes in 3D. Okay. Any questions, by the way, about our plans?
Sorry, when is our midterm?
Okay, we are in week 6 today. So I presume that there will be a lecture in week 7 next time, and then in week 8 there will be a midterm. Although it will be held during the tutorial time, I think we'll still have a normal lecture in that week, followed by midterm. So let's say in 2 weeks from now. Okay,
Okay.
this will give us enough time, by the way, to finalize everything related to lines and planes. This will be a natural point at which we can stop, reflect, and do a midterm. And from that point on, we go on studying second order curves in the plane, second order surfaces in the space, and then how everything is connected with each other through two-body problem in celestial mechanics and applications to astronomy. Okay, but in order to do that, we need to do a very, very elementary stuff to begin with, I would say. Or maybe not so elementary, let's see. Straight lines and planes. We have already seen that a vector, a geometric vector, was defined initially as just a directed straight line segment. So although a vector by itself, as you remember, is not a geometric object, we have discussed that, nevertheless, the notion of a vector is very useful if we want to define a straight line. So how would we define a straight line? A vector is a directed straight line segment of finite length. A straight line is a line which we can say the direction of which is given by that vector, but the line is infinite. So basically, to define a straight line, it means that in a three-dimensional space, we have a certain coordinate system as before, x, y, z, to begin with. And to define a straight line in that coordinate system, we need to give some equation to points constituting that straight line. Unlike a vector, a straight line is a geometrical object, so we can say a certain point with given coordinates x, y, z belongs or does not belong to that straight line. So what can we do? A very natural way of how the equations of straight line can be introduced in the following. So let us fix some given point which we know for sure does belong to this straight line. So suppose that this point, this one, is x0, y0, z0. Okay. Then we have a certain vector which is a vector geometrically represented at that straight line segment. So it goes in the direction of a straight line. Obviously, if we multiply this vector by -1, it would look into the opposite direction, but it will be same straight line. For the moment, let's say this vector is fixed, and I will denote this vector, for example, by d. And this vector d, let's say it has some coordinates which I denote by alpha, beta, and gamma. Then, along with this vector, we can consider the family of all vectors which are collinear to this one. So instead of d, we will consider and introduce a certain parameter t, which is just a real value, and we'll consider vectors td with components, obviously, alpha t, beta t, and gamma t. Geometrically, what does it mean? This means that we stretch or contract this vector using the scaling coefficient t. Or if t is negative, then we change the direction of the vector. But all of them are nevertheless parallel to the original d. And therefore, if all such vectors are moved with their starting point, with their beginning in x0, y0, z0, then the end point is obviously a point x, y, z, which I write as a column vector in this case, which is starting point x0, y0, z0, plus those coordinates of our vector td with arbitrary t, a real number, and therefore we can say plus t times alpha, beta, gamma, where alpha, beta, gamma is indeed our vector d. This is our first equation of a straight line, and a very useful one. It is called a parametric straight line equation. Why parametric? Because there is a parameter t here. We have three coordinates x, y, z, which are actually functions of one arbitrary parameter t. All other parameters here, for example, components of the vector d, alpha, beta, gamma, and the initial point x0, y0, z0 are given. So this is a given constant. This is also a constant. So in general, in order to specify a straight line in a 3D space, we need to specify, first of all, the initial point, any point actually, which belongs to this straight line, but we need to, just any point which lies on the straight line, and the direction of this straight line without distinguishing which actually half line we consider in this case. Any vector which is collinear to our straight line would do. So we need a starting point and any non-trivial vector d which is collinear to the straight line. Once the initial point and the vector are given, then any other point on the straight line x, y, z can be given in a vector notation as a column vector. Actually, what is x, y, z? This is a radius vector of an arbitrary point which lies on our straight line. So this is actually a vector x, y, z. And all such vectors, they, or identifying the vectors with their endpoints, we say this is the equation for our straight line. This should be perfectly clear. That's our first equation we're dealing with. Any questions at that point? Okay, that should be perfectly fine. On the other hand, we can write this equation possibly in another form. If we don't like, for whatever reason, a parametric form, although I would say we have all reasons to like it, you will find probably that the parametric form of our straight line equation is the most easy to deal with, the most useful to apply in solving real problems. So if there are problems, exercises you solve with straight lines, about the geometry of straight lines, it is very, very often useful to consider precisely the parametric straight line form. This is our friend. But if for some reason you don't like this parametric form, we can transform this equation and do something different. So what we can say? We can say that from this equation it becomes obvious that x minus x0, y minus y0, and z minus z0 is proportional to alpha, beta, and gamma. For the moment, assuming that we're in some kind of generic position with, let's say, alpha, beta, and gamma being non-zero, what we can say? We can say that t from those equations in the generic case equals to, first of all, x minus x0 divided by alpha. On the other hand, it is equal to y minus y0 divided by beta. On the other hand, it is equal to z minus z0 divided by gamma, provided that, of course, that alpha, beta, gamma are not equal to 0. This is a so-called generic case. So forgetting about t, we can write the equation of our straight line in this form. So x minus x0 divided by the x component of our directing vector. So alpha is simply projection of our vector d. You remember we start with vector d on x. Beta is the projection of d on y. And gamma is the projection of d on z. We can then write this system of two equations, actually, connecting the three coordinates x, y, and z. Why this form, although very widely used, is less convenient than a parametric form. So this is a non-parametric equation. There is no t parameter anymore. Well, first of all, you see that we can really write our equation like that only in the generic case, when both alpha, beta, and gamma are not equal to 0. Then if any of these coefficients is equal to 0, then we are in some kind of degenerate case, which needs to be considered separately. So suppose that now, let's say degenerate for specific cases. Say gamma is 0. What does it mean? Well, looking into this equation double star, it's really difficult to say what it means. We have a denominator vanishing, so we can't write an equation like that, right? But looking into the original parametric equation star, it is very easy actually to say what it means. Okay, suppose that gamma is 0. Therefore, irrespective to t, we have z equal to z0, right? What does it mean? In our straight line, z coordinate of all points are equal to the initial coordinate z0. What does it mean geometrically?
Can I answer?
Sorry?
Can I answer?
Yes, yes, of course, yes, please.
It is the line we are in. The line in question is parallel to this x, to, for example, z axis.
Not quite. If you see z, so gamma equals to 0, which says z is identically equal to z0. If the straight line, please look at our drawing, is parallel to the z-axis, then z is not constant. We can have z equal to 0, 1, 100, and so on.
Yes, yes.
In that case, actually, this means...
Perpendicular, actually, I guess.
Right.
Yes,
So in this case, the line is parallel to xy plane. That's true. And orthogonal to the z-axis. You are right. So it is immediately clear what it means. So in our non-parametric equation, This would mean that in the last equation, we would have 0 divided by 0, which is again not a nice thing to write, but from the parametric form, we simply know that z is constant, and therefore we can simply drop the last equation and consider only the first two. So x and y are still connected by this type of equation. But we now know that our straight line is parallel actually to the xy plane. Z is equal to z0. And therefore, we're only concerned with x and y being connected by one equation. Z is equal to z0. But no doubt, it's much, much easier to see from the original parametric equation than from a non-parametric one. Moreover, it may also happen that, let's say, gamma was 0, but now what if, obviously, if only one of the parameters, alpha, beta, gamma, is 0, then we would have our straight line being parallel either to xy plane or to xz plane or to zy plane. Okay, now what if two parameters are equal to 0? If in addition let's say beta equal to 0, then again looking to the first equation, we say that y is equal to y0 is equal to a constant value. Okay, so what does it mean?
This line is parallel to x-axis.
The line is parallel to x-axis. Both actually y and z are constant. So I would draw this line like this. Okay, so it is passing at a certain height with respect to z and at a certain value of y. It is parallel to the z-axis. So x is still equal to, let's say, x0 plus alpha t, but because now alpha t is arbitrary, and obviously in that case alpha is not equal to 0, because otherwise the whole vector d is 0. That's what we do not allow. That's not interesting. So the whole vector d is not 0. Then we have a straight line parallel to the x-axis, and it is only just a
I
second.
think it is x-axis, the x-axis itself. If you have y equal to y, if you have beta and the third parameter equal to 0, it is the x-axis itself. It should be. If we...
Not necessarily. Let's be careful here. So we have just a second. So if z is let's explore it a little bit more carefully. If z equals to z0, then the line is parallel to the xy plane.
Oh, I thought the error 0. Sorry, I did not really. I thought like z0 is equal to 0. So that's
not necessarily. No.
Yes,
So we have z being constant in that case, and y being constant. Let's look what it means actually. Z is constant, y parallel to xy plane. Y being constant, so we're parallel to this plane. Y being constant, we're parallel to zx plane. So in that case, our line is indeed to be to consider this, it is parallel to both planes. Therefore, yes, it is parallel to the x-axis, but x is arbitrary. So we have x equals to x0 plus alpha, which is not equal to 0, t, which means that this is an absolutely any number, and therefore we can say x is any real valid number. So z is constant, y is constant, x is any. Yes, it is parallel to the x axis. But viewing this is by far easier if we consider the parametric form rather than we look into non-parametric form and trying to guess what it means when both actually numerators and denominators in some equations are equal to 0, right? Okay, so that's actually about our definition of a straight line. We have considered both ways. As you can see, a straight line is a one-dimensional manifold or one-dimensional geometric object to that end. What does it mean, one-dimensional? So either in the parametric form, yes, 3 coordinates x, y, z are actually functions of one parameter t, others are constants. So 3 coordinates are functions of 1t, which really means that it is a one-dimensional object. Only t can vary from minus infinity to plus infinity. So t is absolutely arbitrary real number here. Or if we consider the non-parametric form, again, in the generic case at least, we have 3 coordinates x, y, z, and 2 equations connecting them together. So if there are 2 equations connecting them, we can solve this system. And again, for example, expressing maybe x and y through z or any other coordinates through 2 coordinates through the third one, or really assigning a value t to these ratios, we return to the original form, and in any case we have just 1 degree of freedom. So if, for example, 1 coordinate is given, then 2 others are computed from the equations. Or if the t parameter is given, then all 3 coordinates are computed from the t parameter. So in fact, straight line is a 1D manifold. This should be perfectly clear. Okay? Now, let us introduce a plane. And with a plane, things would become slightly more interesting because a plane is, well, if a straight line is one-dimensional manifold, then a plane is, what about its dimensions?
Two-dimensional.
Two-dimensional, yes. Two-dimensional manifold. Again, there are several ways of how the equations or the equation of a plane can be written. Let us consider the following. So first of all, if in our, again, 3-dimensional coordinate system, x, y, z, there is a plane, then like for the case in the case of a straight line, we first need to identify at least one point which belongs to this plane. So again, suppose that this is a point x0, y0, z0. Now, if there is a plane, then we can introduce a certain vector which is orthogonal to this plane. Let me denote it by vector n, a normal or orthogonal vector. N is non-zero by definition. And later on, we can consider the situation when, for example, the absolute value of n is equal to 1, but it may or may not be equal to 1. Not necessarily. It might be useful, actually. What does it mean? If this vector is orthogonal to the plane, it means that this vector is orthogonal to all vectors which lie in this plane, or more precisely, because vectors do not lie in the plane, they are not geometric objects, which are parallel to the plane. So that's our point x0, y0, z0, and assume that there is another point, any x, y, z, which belongs to this plane. Then consider a vector. Let me denote this vector by, for example, delta. Delta is a vector which starts in x0, y0, z0 and ends in an arbitrary point x, y, z lying in the plane. Therefore, the coordinates of this vector would be x minus x0, y minus y0, z minus z0. And for an arbitrary point x, y, z lying in the plane, our vector d is orthogonal to the given vector n, because vector d x, y, z lies in the plane, x0, y0, z0 obviously as well. Therefore, vector d is parallel to the plane. I can't say it is lying in the plane because the vector is not a geometric object. And as such, n is orthogonal to the whole plane, and therefore it is orthogonal to the delta vector as well. Which means that the dot product of delta n must be 0. From if our vector n is given by its coordinates nx, ny, and z, from this we immediately get that nx, x minus x0, plus ny, y minus y0, plus nz, z minus z0, must be equal to 0. That the first, by the way, non-parametric equation of a plane. If for a straight line we started with a parametric case, this is a non-parametric equation of a plane. 3 star. Okay. Or expanding the left-hand side and possibly writing instead of nx and y and z some coefficients a, b, c equivalently, we would have ax plus by plus cz, but we remember that in fact a, b, and c are coordinates of a vector which is orthogonal to the plane. Let's say plus d, where d is yet another constant, is 0, where d is, in this case, minus nx x0 plus ny y0 plus nz z0. But in general, we can write our equation in this form. There is a single equation which connects together 3 coordinates, x, y, and z. And indeed, we get a 2-dimensional manifold. One constraint to three coordinates. So 3 minus 1 is 2. We have 2 degrees of freedom here. This equation, by the way, is not very easy to deal with if you would like to express, for example, one coordinate through the rest. So suppose that you would like to really leave 2 coordinates free and express the third coordinate through those free 2. But which? It depends on which coefficient is non-zero. So if a is not equal to 0, then obviously you can express x is minus b over a y minus c over a z minus d over a. If b is not equal to 0, then in a similar way you can express y. If c is not equal to 0, then in a similar way you can express z. So in this case we have 2 free coordinates, and the third coordinate is a function of those 2. But we can't do it in the generic case. We never know which of those a, b, c, or equivalently an x and y and z coordinates would be 0 or non-zero. Okay? And obviously, the length of our vector n doesn't matter. We would get exactly same equation, especially looking into this equation, if we scale our vector n by any factor, for example, multiplying by any lambda, we would get exactly same equation of the plane, and therefore it might be convenient, although not always necessary, really to select a unit vector n, and even if it is a unit vector, then we have a certain degree of freedom, because multiplying it by -1, we would get still a unit vector, and again, exactly same equation of the plane with that unit vector. Okay? Any questions about this equation? No. Alternatively, what can we do? We have already started, you remember, rotations of coordinate spaces. So what we can say is that again there is our coordinate system x, y, z, and there is another coordinate system somewhere which is rotated relative to our x, y, z, and that coordinate system I would, for example, denote by u, v, w instead of x prime, y prime, z prime, just for convenience. Okay? And suppose that it is really this plane uv which is the plane of interest for us. So what we want, using the coordinate transform formulas we have already derived, provide yet another definition, yet another equation for our plane, in this particular case, the UV plane. So what would be the equation of UV plane? You remember that in general, we had x, y, z would be given by a certain matrix A, which is, let's say, a rotation matrix, which is a normal orthogonal normal matrix with determinant of A, for example, equals to 1, although it doesn't matter at all in this case. -1 would do as well. Multiplied by new coordinates u v w plus the coordinates of the new origin in the old system, which is x0, y0, z0, plus x0, y0, z0. Okay, if we are interested in the equations of the UV plane, therefore in the UV plane, W is equal to 0, right? Therefore, what we get xyz equals to our matrix A multiplied by u, v, and 0 plus x0, y0, z0. Or remember that our matrix A was A11, A13, and so on, A31, A33. We would get linear equations for x, y, z, y, u, and v. So in this particular case, x equals to a11u plus a12v, and because w is 0, then it does not occur here. So actually it is only this submatrix, this block a11, a12, a21, a22 occurs here. Okay. Yes, 32, a33. Okay, plus x0 obviously, and y equals to a21 u plus a22 v plus y0. What have we got? Yes, and z, and for that we also have an equation, a31 u, therefore it is not this block but this block actually. A31u plus a32v plus z0. Therefore, we have two parameters, u and v, and with linear coefficients from the matrix A and the initial point x0, y0, z0, we get coordinates of any other point in our UV plane. So what have we got? How is it called?
Parametric equations.
Parametric equations of the plane in 3D. So 4 stars, parametric, we're drawing the American flag, you know, parametric equations of a plane. How would these parametric equations connect with non-parametric ones? So you see here we are using those A11 and so on coefficients of our matrix, whereas in which coefficients we are using? You see, we are using the first column of our matrix and the second column. What is the first column? The first column is precisely, you remember from our linear transforms lectures last time and previous times. So what is the first column? A11, A21, A31.
Is basic vector of a new coordinate system.
Yes. Yes. This is the vector of our u axis, normal vector of the u axis. And obviously the second column is the normal vector of the v axis. So you see, interesting. In the original non-parametric form, we were using the vector which is orthogonal to our plane. So supposedly it would be this normal vector. Let me denote them again as we did I prime, J prime, K prime. So here we are using I prime and J prime. In the non-parametric form, we were using K prime effectively. This K prime is the same as N in our non-parametric form. So the question is, how are they connected to each other? Surely there should be some connection, because you see, otherwise there is a contradiction. We are something counterintuitive. We defined it using I prime and J prime, and that equation was using K prime. Okay, so what can we do about this? Let us, if we got equations like that, so let us, first of all, K prime, we already know is not independent of I prime and J prime. K prime is the cross product of I prime times J prime. So if I prime and J prime are given and they are used in our parametric definition of our plane, then one can argue that K prime is also known and therefore can probably be used in non-parametric definition. Okay, so let us rewrite these equations moving x0 in the left-hand side. So x minus x0 equals to a11u plus a12v. Y minus y0 equals to a21u plus a22v. Z minus z0 equals to a31u plus a32v. Okay. Now again, this vector x minus x0, y minus y0, z minus z0 is a vector which is parallel to our xy plane. So this vector is parallel, sorry, not xy, but uv plane. UV plane. If it is parallel to the UV plane, then it must be orthogonal to n or k prime. So let us multiply both left-hand side and right-hand side of our equation by the vector k prime. But k prime is the same as n, which is normal to UV plane, which is precisely this a13, a23, a33 vector in our matrix. All right? So we multiply by it, making dot product. A13 times x minus x0, this dot product, plus a 23 y minus y0 plus a 33 times z minus z0 equals to what? Okay, let's do it. A13 times a11u plus a12v plus a23 times a21u plus a22v plus a33 times a31u plus a32v. Now let's collect the terms at u and v. We get a13, a11 coefficient at u plus A23, A21, that's U, plus A33, A31, U, plus A13, A12, plus A23, A22, plus A33, A32, V. What is this? Looking at our matrix. This is, what do I think it is? It is a dot product of the first and third column. So it is column 1 dot product column 3. Okay? As vectors. This one is column 2 dot product column 3. What can we say about these dot products? They are 0, both. They are both 0 because columns of our rotation matrix A are orthogonal to each other. Therefore, the right-hand side is identically equal to 0. And now we got what we want. So from this parametric representation, using the I prime and J prime vectors, multiplying the left-hand side and the right-hand side by the normal vector, normal to the UV plane, we get A13x minus x0 plus A23y minus y0 plus A33z minus z0 equals to 0 identically. So we're back to non-parametric representation. And again, in solving problems, you are free to use both actually parametric and non-parametric representation as you see fit. Parametric representations might be a little bit easier to deal with. Furthermore, well, okay, let's make a small break and we'll consider continue our explorations. Break 5 minutes. Okay? You will have time to reflect on this. Okay, getting back to our lecture. Any questions so far?
Excuse me.
Yes?
I just want. I felt like I lost a little bit connection, but in the first, how to say? Could you please go up a little bit in the slide?
Yes. Here?
Yes, or yeah, yes. Thank you.
Okay.
So we just considered like arbitrary u and v and w vectors, right?
Yes, so we consider an arbitrary coordinate system. Well, not exactly an arbitrary. So basically, we're interested in describing the UV plane. So yes, we considered a coordinate system such that the UV plane in that coordinate system is precisely our plane of interest. And the W axis is orthogonal, obviously, to UV plane.
I see. And this is why we transformed the w to 0, so
Yes,
we
of course.
can.
Of course.
Yes. Okay.
So
Okay. So I
precisely.
think everything
Okay.
is clear.
Okay, great. Now we can go a little bit further and we can generalize our equation 4. So you see, in this equation 4, x, y, z are linear functions of two parameters u and v with some coefficients a11, a21, and so on. And these two vectors are actually orthogonal to each other. In fact, this is not even necessary. And you see, we didn't even use this fact. What we used is that in order to make our right-hand side identically equal, that you see that column 1 is orthogonal to column 3. So this is 0. And column 2 is orthogonal to column 3. We never use the fact that column 1 and column 2 by themselves are orthogonal to each other. We don't need that. So we can, instead of considering a fully normal rotation matrix, we can reason the following way. Consider two vectors, for example, u and v, and in our xyz coordinate plane. And again, we're interested in this UV plane, how to describe it. What can we say? We can say that this plane is any vector lying in this plane is orthogonal to the vector which really needs to be orthogonal to the whole plane. So to this W vector, but it doesn't need to be a normal one. It is, how do we make a vector W which is orthogonal to both actually V and U? We did it last time, and it is simply a cross product of U times V. And then it would be exactly same story. So any vector lying in our plane, how can we explain it? How can we express it? Suppose that u and v by themselves are, u and v vectors are not collinear. So u is not collinear to v, and therefore w, which is uv, is not 0. Then any, this is again our point x0, y0, z0. And this is again a point xyz lying in our plane. We can argue that the set of all points x, y, z lying in this plane are such that x minus x0 is equal to some factor u. Let me put it that way. The vector x0, y0, z0 is a linear, the difference x, y, z minus x0, y0, z0 is a certain linear combination of our vectors u and v. So for vectors u and v, I do not introduce I prime and j prime normal vectors anymore because they do not need to be normal. So what I say is that x minus x0, y minus y0, z minus z0 can be represented as some coordinate u times vector u. It's not very nice to use this notation, but both for the coefficient. Okay, I will use different notations. Okay, lambda times vector u plus mu, which is a scalar, times vector v. All those vectors lambda u and mu v are vectors precisely lying in the plane uv, such that these vectors are orthogonal to the vector w. Therefore, we are again in parametric notation for our plane, but please take note that u and v are constant vectors in this case. And instead of uv coordinates as before, we have lambda and mu being parameters. So again, we have a space of 2D parameters applied to arbitrary vectors u and v, such that the only condition is that u is not collinear with v. In particular, this implies that neither u nor v can be zero vectors. And again, we have a parametric expression of our plane. Or if we would like from this equation to get a non-parametric one, then we do it very easily. Again, getting to w, which is a cross product of u times v, we now can write that wx times x minus x0 plus wy times y minus y0 plus wz z minus z0 would be equal to 0, of course. Okay? Because w is orthogonal to u, w is orthogonal to v, and therefore w multiplied by lambda u plus mu v is, of course, 0 as well. So we have played around multiple ways of how parametric and non-parametric equations for a plane can be constructed. In practical situations, select whatever representation is more suitable for your particular problem, for example, better connected to the information given about a particular problem. Okay? And now, let us consider yet another example. We started with a straight line, and then we defined planes, again using parametric and non-parametric equations. But then you can argue that a straight line can also be viewed as an intersection line between two planes. So let's see how we can consider this. Straight line as intersection between planes. Okay. In that case, we need two planes, and let us probably specify them in a non-parametric notation. So we have a1x plus b1y plus c1z plus d1 equals to 0. This is plane 1. And a2x plus b2y plus c2z plus d2 equals to 0. This is plane 2. Okay? If we consider this system of equations together, this means that we're considering points x, y, z, which belong to both planes. And if they belong to both planes, then arguably they should belong to a straight line, which is an intersection line between the two planes. All right? Well, almost. In the generic case, yes. But we need to consider all possible degenerate situations which might occur here. So first of all, let us return to the equation of the plane. Let's, for example, have a look at this one. a1x plus b1y plus c1z plus d1. Do you think that this equation might be slightly, I would say, extraneous, that we have a little bit too many parameters here? Well, if we know that a certain parameter, for example, a1, is non-zero, then we can divide this equation by a1, and we can get, for example, a1 is not 0. Dividing by a1, we get x plus b1 tilde plus c1 tilde plus d1 equals to 0, where b1 tilde is obviously b1 divided by a1, and so on. And from that equation, we can express x, b1 y plus c1z, yes. We express x via the rest of the coordinates. So it is minus b1 y minus c1 z minus d1. In a similar way, if, for example, b1 is not equal to 0, then we can express y via x and z. If c1 is not equal to 0, then we can express z. And finally, if d1 is not equal to 0, then we can't express x, y, or z directly through each other, but we can normalize d1 to 1. And by dividing to it, and we would have a1 tilde x plus b1 tilde y plus c1 tilde z plus 1 equals to 0, which means that having 4 different parameters, different constants here, I would say constants, not parameters, constants a, b, a1, b1, c1, d1 is not really necessary. If at least one of them is not equal to 0, then we can divide our equation by this parameter and get a simple form with only 3 constants. Then the question is, why do we write it that way with 4 constants? Can you tell me, please?
We may have zeros like coefficients which are equal to 0. Maybe a problem than to represent them with only.
Let us say that not all of them are equal to 0, that at least we must have a1 squared plus b1 squared plus c1 squared plus d1 squared is not equal to 0. Because if all of them are identically equal to 0, then we have just a trivial equation 0 is equal to 0, which doesn't define any plane. So at least one of them is not equal to 0, yet we're right. And then we can divide by this coefficient and express our equation with only 3 coefficients. Nevertheless, we normally, in the general case, write the equation with 4 coefficients, A, B, C, D. Why do we do so?
Maybe in case if plane intersect 0 point or not intersect 0 point of our coordinates system.
Well, you know, the answer is very simple in this case. We do it for the sake of genericity or generality, put it as you like, only. If we write an equation like that, we do not care which of the coefficients A1, B1, C1, D1 is non-zero. We know that at least one of them is non-zero, but we don't care which. We can write the equation like that, and we're okay. But if we really consider which of them is non-zero, then this single generic equation actually is split into 4 different cases. And in those 4 different cases, we write 4 different representations of our equation for the plane. So instead of one generic case, we have 4 specific cases. This is simply inconvenient. It may happen that when you really need to come to the detailed analysis of your plane, that you do need to consider those 4 specific cases. But sometimes, and possibly more often than not, we are completely okay with writing just one generic case and not caring about which of those coefficients is actually non-zero. Maybe all of them are non-zero. That's only for the genericity. Okay, so same about the equation of the plane 2, second plane. Now, how can we solve these equations? We have 2 equations with 3 unknowns, x, y, z, which mean that this system of linear equations is what? Underdefined or overdefined?
Undefined.
Underdefined. Underdefined. Which means that in general, we wouldn't be able to uniquely determine x, y, z. And of course not, because we know that the solution is precisely not a single point x, y, z, but the whole straight line. So the solution is a one-dimensional manifold. 1D 3 minus 2D manifold. So precisely a straight line. What can we do? Then suppose that we write down the matrix of this system. So in a matrix form, it is A1, B1, C1, A2, B2, C2, X, Y, Z equals to minus D1 minus D2. Let me put it that way, in the matrix form, all right? What can we say? Look at this matrix. You probably, in your practical tutorials, you remember the Kramer rule for solving systems of linear equations, although you are using this for 3 by 3 systems, and in our case we have something peculiar. we have an undefined 2 by 3 system, 2 equations, 3 unknowns. But you remember what the minor is in a matrix. So from this matrix, we can construct 3 minors of the size 2 by 2. For example, taking the first 2 columns, we can construct A1, B1, A2, B2. Taking the last 2 columns, we can construct B1, C1, B2, C2. Taking the first and the last, we construct A1, C1, A2, C2. Okay? Now, let me denote them by M1, M2, M3. Now suppose that at least one of them has a non-zero determinant. So for example, the determinant of M1 is A1, B2 minus B1, A2. The determinant of M2 is B1, C2 minus C1, B2. And the determinant of M3 is A1, C2 minus C1, A2. Okay? Suppose that one of them is not equal to 0. For example, this one is not equal to 0. What does it mean? It means that we can rewrite our system in the following way. We keep only x and y to be unknown, really unknowns, and z to be a parameter. So we rewrite our system as A1, B1, A2, B2, xy, equal to the right-hand side, obviously, minus D1 minus C1z, where z is any, minus D2 minus C2z. Okay? What does it mean? Because this matrix is non-singular, the determinant is not equal to 0, we can solve this system of equations, and as a result, we get x to be some linear function. That's important. Some linear function of z with constants. So we can say x is, by solving this, I do not do it explicitly, you can very easily do it. Eventually, because we have in the right-hand side a linear function of z, we would have, for example, x is some alpha 1 plus beta 1 z, and y equals to some alpha 2 plus beta 2 z. Okay? By solving this system. We can do it because the left-hand side is non-degenerate. Coefficients alpha 1, beta 1, alpha 2, beta 2, you can easily compute yourself by explicitly solving this system. What have we got? We got the situation when our x and y coordinates are linear functions of the remaining z coordinates. In which case, we can say z is any, x and y are functions of that. So going back into the parametric representation, we can say z equals to t, and x and y are functions of t functions of t according to the given formulas. In that case, we can say that x, y, z is what? First of all, x0, y0, z0 corresponding to t equal to 0. What do we have here? When t equal to 0 or z equal to 0 to that end, then we have alpha 1, alpha 2, and 0. Plus t, which is z, taken with coefficients beta 1, beta 2, and z itself is taken obviously with coefficient 1. So if we got the first minor a1, b1, a2, b2 non-zero, then we can solve our system of equations that way, and we can eventually construct the parametric equation of our straight line, which is the intersection line between our planes. In exactly same way, we can do it if the second minor is non-singular, so we have determinant of M2 is not equal to 0. Only in that case, our equations would be B1, C1, B2, C2, YZ equals to minus D1 minus A1X minus D2 minus A2X. And again, in a similar way, we can solve it in case when the third minor is non-singular. So both, either way, we eventually arrive at a parametric form, if we want, a parametric form for our intersection line between the two planes. Or we arrive at maybe more simple form, because we know that, for example, our parameter t coincides with one of the coordinates. Here t is z, in this case t is x, in this case t is y. That's how we construct the equations for the intersection. It's a little bit unpleasant of how we did it here, because again we have to split our general situation, general case, into three specific cases, depending on which minor has a non-zero determinant. Obviously, if one of them is 0, we can consider, for example, the second one in the hope that it is non-zero. But if both of them, for example, M1 and M2, have 0 determinants, then M3 would have a 0 determinant as well. So that's important to understand, because in that case, it would mean that, what would it mean? If both actually M1 and M2, and you can easily see in that case M3 as well, has 0 determinants. What does it mean?
Can I answer?
Plane
Yes.
does not intersect.
Yes, please tell me.
I think one of my other teammates answer. I don't know.
Yes, please, anyone.
Planes does not intersect.
Well, you are right, which means that
Yeah.
if both, all of them are degenerate, this means that basically the rows A1, B1, C1 and A2, B2, C2 are proportional to each other. Rows being proportional to each other mean that the normal vectors to these planes are collinear, which means that the planes are either, but that's important thing to understand, the planes are either parallel to each other, or, and in this case they do not intersect at all, the solution would be empty, or it might be that it is actually the same plane. For example, A1, B1, C1, and D1 are 1, 2, 3, 4, and A2, B2, C2, D2 are just, let's say, 2, 4, 6, 8. Then both equations are absolutely same, and it is the same plane. In that case, there is no intersection straight line either, but the solution would be the whole plane. So we have quite a few possible cases here. Okay, we're done for today. Next time we'll consider in a little bit more detail, we'll write down the equations for those degenerate situations. We will be able to distinguish between generic and degenerate situations, and then we will also try to consider this example for planes intersection from the cross product point of view, and then you will see that it is actually easier than writing the determinants and solving systems of linear equations. Okay? I would very much like to do it now, but it naturally follows into the next lecture. For today, we are done.
Excuse me.
Yes?
I don't have a question, but like I have more of a request.
Yes, please.
I have tried to read a little bit of the textbook that was afforded with the course, but I feel like it's a really old book. Like it's a little bit how it's written is a little bit annoying to use. Do you have any in mind any other book like?
Oh
you
yes,
could
very much,
recommend?
very much so. You see, what we will do, we have plenty of textbooks. The problem is that I can't put them into Moodle simply because this one is in public domain. It was published in 1980, and under the Russian copyright law, it's not American, you know. In the United States, it is 90 years, but in Russia, it is only 20 years. So the copyright has expired a long time ago, and that's why it is truly and officially in the public domain. There are much better books which are not yet completely truly and officially in the public domain because they're American. But I will put them not into Moodle, but rather in our Telegram channel. And
Yes.
please, yes, use whatever you see fit. Okay?
Okay, thank you. Because it's really old and it's really hard to understand. I guess.
I fully agree with that. Yes, we can do much better than that. I will put much more preferred and recommended books into our Telegram channel.
Yeah, could you please do it as soon as possible? And thank you.
We will, yes, definitely.
Thank you.
As soon as our lecture today is published. Okay. Well, thank you for attention. Thanks a lot, and we'll continue next time with planes intersection and then solving more interesting and more important problems on straight lines and planes. After that, we'll move on to studying two second order curves in a plane, conics. Thank you.
Bye.
Goodbye.
Thank you. Goodbye.
Goodbye. Thank you.
Goodbye.
Goodbye. Thank you.